Hello everyone. Welcome to IIT and GATE classes. This is lecture 13 on operating system. And in this lecture, we are going to start classical problems of operating system. Okay, so we will study three problems of operating system. The very first is known as producer consumer problem. Producer consumer problem. You might be thinking that we have already studied this problem, then why we are studying it again? So now we will study it with the help of semaphores. Okay, so let me write that in bracket. So we are going to study that problem with the help of semaphores. That means solution to producer consumer problem with the help of semaphores. Okay, yes. And the second problem which we are going to study is readers writers problem. Okay, reader writers problem. Okay, that is also very important, and we are again same scenario, we are going to study it with the help of semaphores. And the third problem is dining philosophers problem. Dining philosophers problem. Okay, that is again we are going to implement it with the help of semaphores. So basically with the help of semaphores we are going to implement these three problems. Okay, yeah, so one by one let me start it. So the very first is producer consumer problem. Take snapshot, I will jump to the next slide. Okay, so the very first is producer consumer problem. Okay, yeah, so what producer consumer problem is saying. So first let me build the background, or you can say what are the variables or something which we are going to use. So we are going to use full and empty. These are counting semaphores. Counting semaphores. Okay, yeah, so let me first tell you, let me jump to the next slide and let me tell you what are counting semaphores and all. So actually semaphores are of two types. One is known as counting semaphore and another is known as binary semaphores. Okay, counting semaphores means they can take value from minus n to plus n. That means integer value they can take. Any integer value which you want to give, you can give them. And then there is binary semaphore, as the name suggests, it can take value it only 0 or 1, only two values. Okay, so for example we say mutex is binary semaphore. Generally mutex word is used for binary semaphores only. Okay, so mutex is used for binary semaphores. And obviously you can take any binary semaphore whose name is x, y, z, whatever way you want you can give the name. But generally I'm saying whenever you see mutex in any program, you should immediately say, okay, it is a kind of binary semaphore. Okay, so mutex is a trademark symbol for binary semaphore, like this you can think. Okay, so in any program you see mutex, you will immediately say, okay, it is nothing but a binary semaphore. Okay, so binary semaphore can take value only 0 and 1. So for example, if we say mutex value is 1. Okay, mutex value is 1. Okay, that means we have initialized this mutex with the value 1. So now if any process do v mutex, so what do you think? Its value should become 2 because 1 plus 1 v mutex means what? We will increment the value, but it will still remains 1 only because it is a binary semaphore. If it was counting semaphore, then 1 will become 2 and so on. Okay, so now again, if any process do v mutex, no problem at all. Its value will remain 1 only and so on. Dot, 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 dot. So even if 1000 processes do v mutex, then its value will remain 1 only. But in case of counting semaphores, if you can say x is a counting semaphore, x is a counting semaphore and we say x is initialized to value 1. Now if we do 10 times v mutex, sorry, vx, 10 times you do vx, so its value will become 10. Okay, obviously, sorry, 10 times increment now, so it will become 11. Okay, one time increment it will become 2, 2 times then it will become 3 and so on. So 10 times increment it will become 11. I hope you have got it. Now this is very simple point. Okay, so similarly, if you say 10 times vs and then 5 times px, 5 times px, so 5 times it will be decremented. So 11 minus 5 is 6. So finally 6 is the answer. Are you getting it? This type of question have been asked in GATE many times. So we have a counting semaphore whose value is n. Okay, or you can say whose value is 10. Okay, let me say like this. Okay. So these type of questions have been asked in GATE many times. So what they are saying is, so we have a counting semaphore whose value is x, or you can take any numerical value also. For example, it's counting semaphore x. We have a counting semaphore x and whose value is initialized to 1. Now we are doing say 15 V operations, 15 V operations and 10 P operations. Okay, in any sequence you have done it, or rather you should say 15 V operations, then 10 P operations. So what will be the value of x, final value of x? So final value of x will be, so I have maintained a sequence also. 15 V operations are done first and then 10 P operations are done. So finally, totally see 15 times incremented and 10 times decremented. So obviously your final net result will be 5 times incremented. So 1 will be 5 times incremented. That means 1 plus 5 that is equal to 6 is my answer. So simple. So this type of question has been asked in GATE many times. Okay, so I hope I have made the point clear. Take snapshot and I will jump to the previous slide now. Okay, yeah. So now what we were studying, so full and empty, these were counting semaphores. Now I think you have got it. What is this counting semaphore and all? Okay, and next P and next C. Next P, next C. They are what? They are item type. They are of item type. Okay, I think you already remember. If you have studied producer consumer problem from my previous lectures, you have got that. Now, next P was what? In which next produced. That means producer will produce item in next P. Next C means next consume. So consumer will consume item with the help of next C. I think you have got it. Okay. Yes, and next we have a variable full. Okay, sorry, full was our counting semaphore, na? So full is initialized with 0. Okay, and empty is initialized by n. Empty is initialized by n. Next we have mutex. Mutex is again, I think you already know, it is binary semaphore. Okay, yeah, and mutex is initialized to 1. Okay, these are the variables which we are going to use in our program. So full initialized to 0 means initially, obviously buffer is empty. Okay, and empty is n means n slots in the buffer are empty and 0 slots in the buffer are full. You can think like that. Okay, why? What do you mean by full is initialized to 0? That means 0 slots in buffer. Slots means elements. You can think like that. Okay, for example, this is our buffer. So it is having say 4 slots. Okay, so 0 slot in buffer is full. Okay, and this means n slots in buffer is empty. N slots in buffer are empty. N slots in buffer are empty. I think you have got it. Okay, so these are the you can say variables which we are going to use. Take snapshot. I will jump to the next slide now. Okay, so now I'm going to write the code for it. So how we are going to write the code? So for example, first I'm going to write code for consumer process. So what consumer process is saying? Repeat until false. Repeat until false means infinite times it is going to repeat. Okay, so forget about syntax and all. Okay, so we have just written a loop, that's it. Okay, so because it is an algorithm, so no problem. So we will say p full. Okay, and then we will say p mutex. Okay, and then we will these 3 dots means we will write the code. Okay, it's just an algorithm. So remove an item from buffer. Remove an item from buffer to next C. Buffer to next C. Let me put it little bit here. Yes. Now it's okay. So remove an item from buffer to next. See, these three dots means this is the code for this. Okay, so how you are going to remove and so on, it's your wish, it's your implementation. We are not going into that. So I'm just giving you idea, or you can say the algorithm. Okay, p mutex, and then we will say v mutex. Okay, and then we will say v empty. Yeah, so this is the code for consumer. So let me show you line by line what exactly we are doing. So first line, p full. So obviously when consumer will come, it will first decrement the value of full, because now full is going to decrease. Are you getting it? Full means what? Say this. Full means 0 slots in buffer are full. That means full is saying number of slots which are full. Okay, so for example, full is 4 means 4 slots are full. Empty is n means all are empty, and so on. I think you have got it. Na? These are very simple things. So p full means, first of all, it will decrement the count. That means it will say your number of full slots are going to be decreased by 1. That's why we are doing p full. If you do not know what is p and v, please watch my previous lecture. Okay, so p full has been done. So now see this, we have done this p mutex, v mutex. That means it should be done in mutual exclusive fashion. And I have told you many times, buffer will be accessed by only one process at a time. So that's why we have written that in p mutex and v mutex. I think you already know. Okay, so PSCS, VS we have done. Are you getting it now? PSCS, VS. And I had told you S is initialized to 1. So mutual exclusion was guaranteed. No doubt bounded weighting was not guaranteed, but it hardly matters. For mutual exclusion only, we have done this part. Okay, P mutex, V mutex. If you do not know what are these, please watch my previous lecture. Okay. So now finally it will do v empty. V empty means now empty slots are going to increase. Okay, that's why it has done v empty. And how many are increased? It will be increased by 1 only, because now it has consumed, consumer has consumed the item. Since consumer has consumed the item, so empty will increase by 1 and full will be decreased by 1. So first of all, it has to check p full. Okay, for example, if nothing is there, or you can say buffer is empty, then full will be 0. So if consumer comes first, it will say p full. Full is 0, so obviously it will go into infinite loop till full is full get value 1, 2, 3, and so on. Are you getting it? So if full is 0, then consumer will keep on waiting here, and that is for sure. Consumer should wait, because if nothing is there, then what will be consumed? So we do not know. So that's why in order to guarantee that consumer cannot come first, we have done like this. Okay, so obviously producer should come first, consumer cannot come first. How consumer can come first? If consumer comes first, then what it will consume? Are you getting it? See, actually do not get confused. No doubt consumer can come first, but if it comes first, then it will remain in this loop only. Okay, so my intention is to say consumer should not come and access the buffer. That is the basic thing. Okay, so if consumer comes first, it will keep on rotating in this infinite loop. That means it cannot, obviously when item has not been produced, how it will be consumed? That is very basic thing. Na? So first item should be produced, only then it can be consumed. So consumer should not come first and access the buffer. That's why we have written p full first. So we are going to indirectly we are going to check whether something is there in the buffer or not. If something is not there, that means full is 0. So consumer will keep on waiting, and so on. I think you have got it. I should not repeat it again and again. Okay. So this is the code of consumer. Now let me tell you the code for producer. Okay. So please take snapshot. I will jump to the next slide. So let me write code for producer. So how producer code will look like? I will say repeat, same thing, repeat until false. Okay. That means infinite loop. Okay. So producer has to produce item. Na? So first of all, I will say produce an item in next P. Okay. So it is going to produce an item. Then it will say P empty, then P mutex. Okay. And then add next P to buffer. V mutex. Don't worry, I will explain you all the things. First, I'm writing the code. Okay. and then we will say v full. Okay, so now please check what producer is going to see. What producer is going to do? It will blindly produce an item in next P. Whether buffer is full, empty, it hardly matters to me. P will directly come and produce an item in next P because producer work is to produce an item. So it has produced an item in next P, and now it is checking P empty. So if empty is 0, that means 0 slots are empty in our buffer. So directly, indirectly, producer should have to wait. So if empty is 0, that means producer will keep on waiting here and cannot cross it. Okay, so now assume that empty is say 1, 2, 3, 4, something like that. Positive number is there, so it will decrement the value of empty. Why producer is decrementing the value of empty? Because now it has produced some item and it is going to put that item in the buffer. So obviously empty will be decremented and full will be incremented now. So see this, we have done full incremented. Okay, anyhow, so p empty it has done. So now see this again, p mutex, v mutex. So directly, indirectly, we buffer should be accessed in mutual exclusive fashion. That's why in producer we have written this. Okay, so now finally we will do v full. Okay, why v full? Because full should be incremented by 1 now. Why full should be incremented by 1? Because producer has now produced an item. So since item has been produced and put inside the buffer, so full will be incremented. Are you getting it now? So what producer is doing? Producer is it is decrementing empty and incrementing full. What consumer is doing? Consumer is decrementing full and incrementing empty. These are very basic thing, and I think you have got it. Okay, so finally, this is the code for producer. Okay, so you can check it out. Take snapshot. So I think you have got it. So now they can work parallelly also. Obviously we have written the code so that they can work parallelly. Okay, so when consumer will come, it will do p full and it will consume an item and then it will do v empty. Okay, it will do v empty and then repeat until false. It will keep on doing. Producer is also doing like that only. Producer will blindly produce an item and then in p mutex, it will say add next p to the buffer and then v full. Finally it will increment the value of full and until false. So it will keep on doing like that. Okay, repeat until false. So this is a loop now. This is a loop, infinite loop. Okay, and in depth, I think it's self-explanatory. These are very simple and basic things. You can check it out yourself also. Okay, so that's it. So you can take snapshot and I will jump to the next slide now. Okay, so the next problem which we are going to discuss is reader writer problem. Readers, writers problem. Okay, what this problem is saying. So I think you already know what is reader writer. That means what reader is a process which want to read something, like you can say a file or variable and so on. And writer is a process which wants to write that thing. Okay, so you can take example of a file. This is a file and reader process wants to read it, but writer process wants to write it. So obviously when writer is writing writing something into the file, then no reader process can read that and no writer process can write that. Okay, so simultaneously write should not be allowed now because it will mix the code. So better is only one process should be allowed to write an item or write something into the file. Only one process should be allowed to write something into the file. And when one process is writing, then no other process can read or write that file. Are you getting it? Similarly, one reader process is reading the file, then other reader process can also come and read the file. Reading is allowed now because they are reading, they are not changing the code and all. So at a time, multiple reader process can read the file, but when they are reading, no writer can come. I think you have got it now. So you can write that if you want to write, then you can say when only one writer process should be allowed to write the code. Only one writer process should be allowed to write the code. And when writer process is writing, no reader process can come to read the code. When writer process is writing something, no reader process should come to read the code. Similarly, we can allow multiple reader process to read the code. We can allow multiple reader processes to read the code, because they are not changing it. Because they are not changing it. And when reader process is reading the code, when reader process is reading the code, then no writer process can come to write the code. Then no writer process can come to write the code. Okay, so I think you have got it. So now let me show you the things which we are going to write here. So we have two semaphores, right, and mutex. Right and mutex are binary semaphores. Mutex, as soon as you see the mutex, you will say, okay, it is a binary semaphore. Binary semaphore, and it is initialized to 1. Okay, we have a read count variable. Read count is integer variable, and it is initialized to 0. So for reader process, I'm writing the code. For reader, what you will say p mutex. P mutex. Actually, yeah. So we have p mutex. Okay, and then we will say read count plus plus, or read count is equal to read count plus 1, whatever way you want you can write. So I'm writing in a shortcut manner read count plus plus, and then we will say if read count is equal to 1, then p write, wrt. Okay, p mutex. And then we will say we will write some code to read. 3 dots means you will write some code how process is going to read and all. And then we will say p mutex read count minus minus. If read count is equal to 0, then we write, and then we will say v mutex. Okay, yeah. So this is the code for reader process. Don't worry, I have just written the code so that you get more clarity. Yes, so what reader is going to say, it will say p mutex v mutex. So see this is for mutual exclusion. Okay, so I think I have told you many times now, mutex has been initialized by 1. If mutex has not been initialized by 1, it is a binary semaphore, by the way. And if it is initialized by 0, so obviously no process can come here now. This you can think of it as a critical section type of thing. Okay, so only one process should come here. So for that we have initialized mutex by 1. Okay, so what we are saying, read count plus plus. Read count plus plus means read count will be incremented by 1. Now we will say if read count is equal to 1, then p write. See this, actually why we are doing read count plus plus in mutual exclusive fashion, because if multiple process will come to do read count plus plus, then obviously race condition will come, because read count is a shared integer variable now, so multiple process can access this, and the moment multiple processes will access it, it will create problem for us. Race condition will come and all. If you want more clarity, you can watch my previous lectures over it. Okay, so the day when we started critical section problem and all, in that lecture I have discussed all these things. I think lecture number is 10, 9 or 10, you can watch. I do not remember that, but you can watch those lectures, you will get more clarity. Okay, so read count plus plus should be done in mutual exclusive fashion, because it is not a single line. We have to do 3 lines for it: mov r comma count, okay, then inc r not, and then I think you already know we have done these things now. mov r not comma count, okay, inc r not, okay, and then mov count comma r naught. So r naught value will be go to count and so on. So if one process has done till this point, okay, and interrupt comes and so on, I have told you all these things. Okay, please watch my previous lecture. I have just given you a small hint here. Okay, so the basic thing is read count plus plus should be done in mutual exclusive fashion. Okay, now if we say if read count is equal to 1, initially read count is 0 now. If read count is equal to 1, that means one reader process is reading. Read count is equal to 1 means one reader process is reading. Then immediately I will say p write. P write means what? Write is initialized to 1, na? Write and mutex both are initialized to 1. So p write means what? Write will become 0. So the moment write will become 0, now writer process cannot come. Why writer process cannot come? So I will write the code for writer also. See, this writer code is very simple. It will say p write. It will say p write and then write the code. You will write something here, whatever way you want. Okay, so these are algorithms now. These 3 dots I'm repeating again and again. These 3 dots means you will write here a big code that how process is going to write and so on. Okay, and finally we will say VWRT. And it is not our interest. No competitive exam will say how write code will be written and all. This is not our interest. So you should just think that something that process is going to write something in the file and so on. Okay, in write something in file, variable, whatever way you want, you can implement it. Okay, so we are just giving you algorithm. Okay, so the moment it has done p write, reader has done p write, so write has become what? 0. So now writer cannot come. Okay, so the very first reader will come and it will shut down the door for writers so that writer cannot come, or you can say it will apply lock on writers. Okay, then it will do vmutex. Vmutex means so that other reader process can come and it can increment read count and so on. Okay, so now the reader process has come here, so it will read. Okay, so now for example, if one process is reading here, then other reader come, then it will do the same thing. It will do pmutex. Okay, mutex has become 1 now because it has done vmutex. So mutex has become 1, so it will decrement it. It will increment the read count by 1. So now read count will become 2. Now it will say if read count is equal to 1, no, read count is 2 now. So it will not do p write. Okay, because if it do p write, then it will keep on rotating here itself. It cannot come here. Okay, so obviously only first reader will do p write, other will not do. Okay, so finally it will not do p write, and it will do vmutex and it will come and start reading. I think you have got it. If you have any doubt, then you can think like that. Okay, if you want me to do okay pictorially, then you can do like this. Mutex, it is initially 1. So when first reader comes, it will do p mutex. Mutex will become 0, and then it will say read count plus plus. So RC I'm writing. Okay, so RC will become 1. Are you getting it? Initially it was 0, it will become 1 now. Read count is 0 now. See this. So now it will become 1. Okay, and if read count is equal to 1, yes, it is 1, so it will do p write. So write initially it was 1, so now it has become 0. Why write was initially 1? See this, I have said this thing. Okay, so now it will do vmutex. Doing vmutex means what? It will become 1, and then it will start reading. So first process has come here and it has started reading. Okay, now when the next process comes, when the next reader comes, it will again do pmutex. Pmutex means it will become 0. Now read count plus plus, so read count will become 2. So now 2 is equal to 1, no, so it will not do read count. Are you getting it? 2 is equal to 1, no, so it will not do p write, and it will do simply vmutex. Vmutex means what? It will become 1. Okay, so that other process can come now. That's why it is doing vmutex, and then it will start reading. So second process has started reading. Okay, are you getting it? Second process has now started reading, and so on. Multiple processes will come and they will start reading. Okay, so now when one process or multiple processes have you can say completed the reading process, then what should be done? Then obviously they will decrement the read count. Now same problem will come again. So if multiple processes leave this reading type of thing and they just want to come out, then they will decrement the read count. And if multiple processes start doing read count decrement, then again same problem will come. I think I have told you many times now. Just like read count plus plus should be done in mutual exclusive fashion, similarly read count minus minus should be done in mutual exclusive fashion. So we have written that in p mutex and v mutex. Okay, so yeah, so mutex is 1. Okay, so it will decrement it, it will become 0. Okay, and then read count will be decremented. Read count, say for example it was 2, it will become 1. Okay, and then you will say if read count is equal to 0, then we write. We write means what? You are opening the door for writer process. When read count will be 0, read count 0 means no process is reading here. So if no process is reading here, then obviously you will do we write. That means you will open the door for writer. Okay, yeah, and finally you will do vmutex and come out of it. So vmutex means it will become 1, and a process will come out of your reader process will come out here. I think you have got it. Okay. Yeah. So this is the complete scenario. And obviously, when some process is incrementing read count, then no process can do read count minus minus, because when some process is incrementing, then that means what, mutex will be 0. When mutex will be 0, then no process can enter here. Are you getting it? So this and this should be done in mutual exclusive fashion. So it's just like that. When one process is entering here, then no process can exit from here, because if one process is entering and another process is exiting, then one process will be doing incrementing, another will be doing decrementing. That will obviously create problem. Okay, so race condition will come. So that's why what we have used. So we have used here same mutex only. Are you getting it? So when one process is here, then no other process can come out of this critical section. I think you have got it. Okay. So and anyhow, you this read, you can think of it as a critical section, but actually mutual exclusion is not there now, because multiple processes going to read it. Okay, and it is very basic also, because multiple processes can read now. They are not changing the code, so what is the harm? They can read it. Okay. Yes, and read plus read count plus read count minus minus, this is obviously critical section. Okay, because when one process is doing read count, then no other process can do this read count plus, and no other process can do read count minus minus, and so on. I think that is very obvious thing. I'm not going into much more details and all. Okay, so that's it. So for writer process, code is very simple: p write and v write. Okay, so now you can see like this also. So when writer process comes, it will do and assume that write was 1, initialized to 1 now, and initially writer comes first. So when writer comes, then it will do p write and it will start writing. When it is writing something, it can be a file or variable and so on, then can reader come? So let me see. Reader will not come. Why? Because it will say p mutex. Okay, mutex will become 0. In mind, you can imagine the things. Mutex will initialize to 1 now, mutex will become 0, read count will be incremented, read count is equal to 1. Yes, read count is equal to 1 only. Then it will do p write, and the moment it will do p write, it will stop here itself. Okay, are you getting it? It cannot go further. Why? Because now write was 0 na, that's why p write has been done, and then process is writing na. I think you have got it na. When writer is writing, that means what, write is 0. When write semaphore is 0, then how it can do p write? It cannot do p write, and so obviously it cannot go and read the file or variable. I think you have got it. Okay. If and again I'm repeating, if you have any doubt, what is p write, what is v write, and so on, what is p operation, what is v operation, you can watch my previous lecture on semaphores. You will get more clarity. Okay. In the previous lecture itself, I have discussed semaphores and all. Okay. Yeah. So I think you have got the code. So rest, it's all up to you. The more you think, the more you get. That is the basic scenario. Okay, so try to imagine other scenarios and you will get more clarity. So for example, if one writer is there, can another writer process can come? See, if one writer is here, that means obviously write is 0. So when write is 0, other writer process cannot come now, because it has to do p write, so it will stuck here. Similarly, reader will stuck here. I think you have got it. Okay, yeah. So and you have got it now. When read count is equal to 0 means no process is reading something here, so it will do v write. V write means what? Now it has opened the door for writer process, so that writer process can come and write the code. Okay, so everything I have put on the one slide, you can take snapshot, and I will jump to the next slide. So I hope you have taken the snapshot. Let me jump to the next slide now. Okay, so the last is dining philosopher problem. So third problem we are going to discuss is dining philosopher problem. Dining philosophers problem. Okay, so let's discuss this problem. So what see the actually it is related to deadlocks. Okay, so basically you can think of this problem as background of deadlock topic. Okay, yeah. So what dining philosopher problem is saying, so we have some philosophers. Okay, so they are dining philosopher now, so they are sitting on a round table. Okay, so philosophers are sitting on a round table. So we have philosopher number 1, philosopher number 2, philosopher number 3, philosopher number 4, and philosopher number 5. Okay, so and we have Chopstick, Okay, so the philosophers are sitting on a round table, and in between that they have a rice bowl, or whatever you want, you can keep it. Okay, whatever is your interest, chomin bowl, rice bowl, and so on. So we have a rice bowl, and they have only two things. Philosophers will have only two things. They will do only two things. One is thinking and another is eating. So thinking means philosopher P1 is thinking, that means it is not eating. Okay, or he or she is not eating. Okay, and another state of philosopher can be he or she is eating something. Okay, so how he will eat? So it will pick this chopstick, and it or he or she will pick this chopstick. So both chopsticks it will pick, and it will put this chopstick into the bowl, and it will try to it will try to eat. Okay, like rice or chomin and whatever they want, they can eat. Okay, so basically the basic thing is that P1 need both the chopstick. Obviously it need both the chopstick to eat something. Okay, similarly for P2 we will write chopstick. Okay, yeah. So P1, this is C1, this is C2, this is C3, C4, C5. Okay, so now the basic thing which you should know is P1 is sitting like this. So his or her face is towards the rice bowl. P2 faces towards the right bowl, and so on. So P1, since P1 is facing towards this rice bowl, so this will be his right chopstick and this will be his left chopstick. Are you getting it? P1 right chopstick is C1 and P1 left chopstick is C2. Similarly, P2 right chopstick is C2, left chopstick is C3, and so on. Okay, I think you have got it now. P3, let me circle that. Okay, because it might confuse you. P1 is this, P2, P3, P4, and P5. Okay, yeah, so P3 right chopstick is C3 and left is C4. P4 right chopstick is C4, left chopstick is C5. P5 right chopstick is C5 and left is C1. I think you have got it. This is the basic scenario. So now what they are going to do is, so see this. Okay, so and rather first of all I should give you a formula. Okay, so for CI, for PI, let me write it like this. For PI, CI is the right chopstick. I think it is very obvious. For P1, right chopstick is C1, P2, C2, P3, C3, and so on. Okay, and for PI, what will be the left chopstick? If you say +1, then you are wrong. Actually, P1 left chopstick is C2, P2 is C3, P3 is C4, P4 is C5. Till here, no problem. But what about P5? P5 left chopstick is C1. Okay, so how we will say? We will say C. So this is circular fashion. So we will say I +1 mod n. That is the left chopstick. Okay, so you can put the value. So for example, for PI, so for P5, you should put directly. For P5, it will be 5 + 1, that is 6. 6 mod, and n means what? Number of philosophers. Okay, or number of chopstick, whatever way you want, because number of philosopher and number of chopstick are same. So n, you can think of it like a philosopher or chopstick. So let me put that chopstick. Okay, so I +1 mod n. So 5 chopsticks are there. So 5 + 1 mod 5, that will be 1 only. So yes, so P5 left chopstick is C1. I think you have got it. So this is the basic formula. Okay, so mod n we have to do again and again. We have to do mod n for circular fashion. I have told you many times. Okay. So yeah, you can take snapshot, and now I will going to write the code for it. Okay, take snapshot. Yeah. So you can think chopstick is an array. Chopstick is an array of binary semaphores. Binary semaphores initialized to 1. Okay, so chopstick 0 is initialized to 1, chopstick 1. Okay, and you can think from starting from 1 only. Okay, because we are not starting with 0. So chopstick 1 initialized to 1, chopstick 2 1, chopstick 3 1, 4 1, 5 1. So all are initialized to 1. So chopstick is an array of binary semaphore initialized to 1. Forget about syntax and all. I'm just giving you the concepts. Okay, so how we are going to write? I will say pi. You will say p chopstick p chopstick I, and then it will say p chopstick I plus 1 mod n. Are you getting it? Say this. What do you mean by this? P chopstick I, that means it has picked the chopstick number I, pi. So p1, if I'm talking about p1, so it has picked the chopstick number 1. That means what? See, and this is very obvious. For example, if we are saying about p1, so we will assume all are right-handed person. Right-handed means what? P1 will first pick the right chopstick, and then it will pick the left chopstick, and then it will try to eat. So when P1 has picked the right chopstick, then obviously P5 cannot pick its left chopstick. Why? Because P1 has already taken it. So obviously chopsticks should be accessed in mutual exclusive fashion. They will not share it, na. So see what is see, if you say all the philosophers are persons where they are very much well mannered. So what P1 will do? P1 will first pick the chopstick number 1. That means it's right chopstick, and then it will pick the left chopstick, and then it will try to eat. And after eating, it will properly wash these chopsticks and put at their proper places. And then so that when other philosophers, for example P5, wants to eat, then he or she can pick the chopstick 1 and then chopstick 5, and then he or she can eat. Okay, let me say it properly. P5 first, all as we are assuming all are right-handed persons, so P5 will first pick the right chopstick, that means C5, and then it will pick the left chopstick, that is C1, and then it will try to eat. I think you have got it, no? Yes. So P4, what P4 will do? It will first pick the right chopstick C4, and then it will pick the left chopstick C5, and then it will eat, and so on. So are you getting it, no? So when P1 is eating, P5 cannot eat, because P5 can obviously pick its right chopstick, but its left chopstick is with P1. So when P1 is eating, P5 cannot eat. Similarly, when P1 is eating, P2 cannot eat also. Why? Because P2 wants, P1 is holding both C1 and C2. So when P2 comes, P2 has to pick the C2. P2 cannot pick the C2. I think you have got it. Yeah. So first of all, it will pick the right chopstick. Let me write it in the comment. All are right-handed person. So it will pick the right chopstick, then it will pick the left chopstick, and then it will start eating. So for eating, you can write the code and all. It is a simple algorithm. So it will eat. Okay, after eating, what it will do? It will do V chopstick I. So V chopstick I means now he or she is saying that, okay, I have washed the chopstick and now you can use it. Okay, now I do not want to use it, I have washed it, so you can use it. Okay, they are very manner persons with having lots of manners. So they will first eat, then they will wash, and then they will eat. Okay, so we chopstick I plus 1 mod n. Okay. So I think you have got it. So now since it has picked the right chopstick, then left chopstick, then after eating it will again put back, after washing it will put back right chopstick and then left chopstick. Okay, so right and then left. Right picked, you can think like that. Right picked, left picked, right left right washed and put back. Okay, left washed and put back. After washing, it has put back. I have just imagined the things that after washing and all, this is not given in the algorithm. I am just giving you small idea, okay, by my imagination and all. Okay, so they are washing and then they are putting back. So I think you have got it. So this is the code for each and every philosopher. So now let me check whether it is deadlock free solution or not. Deadlock free. So how we are going to check deadlocks and all? So I have told you many times. Now we have to imagine line by line interrupt. So you might think like that. So P1 comes first, then P1 will pick the right, then left, then it will eat, and then it will leave. So like this, P1 will come first, it will pick the right chopstick, then left chopstick, it will eat, and then it will put back. Then P2 come, P2 will pick the right chopstick, then left chopstick, it will eat, and it will put back, and so on. So obviously everything is fit and fine, everything is smooth. Okay, but what if all the philosopher wants to eat at a time? Okay, so if all the philosopher wants to eat at a time, so line by line interrupt we will imagine. So P1 will come first and it will pick the right chopstick. Okay, that means this thing. P1 will come first and it will pick the right chopstick. Then we will imagine we have an interrupt. Okay, and control goes to P2. Control goes to P2. P2 will pick its right chopstick first, that means C2. And line by line interrupt now. So here we will imagine interrupt, and then control goes to the next philosopher. Then P3 will pick the C3 and so on. So try to imagine P1 has picked C1, P2 has picked C2, P3 has picked C3, P4 has picked C4, P5 has picked C5. So all the philosophers, one chopstick, they all have, you can say, picked. Now what will happen? So obviously all the chopsticks are over and each and every philosopher has picked one chopstick. Now P1 is waiting for C2. Why? Because P1 left chopstick is C2, but C2 is with P2. Similarly, P3 is holding C3 and waiting for C4 because C4 is with P4. Okay, P4 is holding C4 and it is waiting for C5. Why? Because C5 is with P5. So P5 is holding C5 and waiting for C1 and so on. I think you have got it. Okay. Yeah. So obviously it will be a deadlock. Why? Because P1 is holding C1 waiting for C2. Please check this. Okay. So each and every chopstick. So let me write that if you have any doubt. So if all philosopher wants to eat at a time, if all philosophers wants to eat at a time, then you can imagine these all were you can say binary semaphores, no? Chopstick and is an array. So C1, okay, because counting has been started with 1, na? C1, C2, C3, C4, and C5. So initially all were 1 because they are initialized by 1. Yeah. So what P1 has done? P1 has picked its right chopstick, that means C1. So now it has made 0. Similarly, P2 has made it 0, P3 has made it 0, P4 has made it 0, P5 has made it 0. So all are 0 now. So now when Pi, or you can say P1 wants chopstick this I plus 1 mod n. So I is what now P1 na? So 1 plus 1, that is 2. 2 mod 5, that is 2. So it wants chopstick number 2. That means it's left chopstick, but chopstick number 2 is 0. So it has to wait. Similarly, all process will keep on waiting here itself. Okay, all process will keep on waiting here itself. So nobody can eat. So obviously it is not deadlock free solution. Okay, so it is not deadlock free solution. Not deadlock free solution. And when deadlocks are when deadlock is coming, when all philosopher wants to eat at a time. When all philosopher wants to eat at a time, then only deadlock will come. So even if when one of the philosopher does not wants to eat, for example, if I say only 4 philosopher wants to eat, then there will be no deadlock. You can think like that. Please try to follow here. So if P1, P2, P3, P4 all wants to eat, okay, except P5, P1, P2, P3, P4 wants to eat, then what will happen? So P1 will pick C1, P2 will pick C2. One line by line interrupt. Please try to imagine. P3 will pick C3, P4 will pick C4. Now interrupt comes, P1 wants to pick C2, but C2 is with P2. P2 wants to pick C3, but C3 is with P3. P4 wants to pick C5, but C5 is free. So since C5 is free, so P4 will eat properly, and after eating, it will release C4 because it has eaten. So it will release the you can say chopsticks, but it will properly wash and leave them. So are you getting it? Now P4 has eaten, so it will leave the chopstick. One day, after 1 day or 2 day, 1 day and 2 day, I'm asking you very extreme cases, because no philosopher will eat for 1 or 2 days continuously. After say 10 minutes, 15 minutes, okay, so P4 will leave the chopsticks. The moment he leaves the chopstick, P3 will pick C4. He will eat, and then it will release C4. P2 will eat because C3 has been released by P3. P2 was waiting for C3 now, so P2 will eat, and then P1 will eat. So in reverse fashion they will eat. So when P1, P2, P3, P4 all wants to eat at a time, then first P4 will eat, then P3, then P2, then P1. Okay, yeah, so there is no deadlock. Please follow properly. There is no deadlock. Okay, yeah, but once all wants to eat at a time, then there will be a deadlock. So I think you have got the point. So the point is that if all philosopher wants to eat at a time, then there will be a deadlock. But if all philosopher does not want to eat at a time, like even if 4 philosopher wants to eat at a time, no problem, there will be no deadlock, and they will eat in the reverse fashion. Okay, now what will happen? So what is the solution? So I want to make a deadlock free solution. So deadlock free solution will be very simple. Okay, so what we can do, so there will be a mutual understanding between all the philosophers. So they will say that even philosophers are right-handed and left philosophers are left-handed. Are you getting it? So let me write it. So solution can be solution to deadlock. Solution to deadlock can be even philosopher, right-handed, and odd philosopher, left-handed. If there is this kind of you can say mutual understanding between them, then obviously there will be no deadlock. Okay, so how we are going to check it? So let me write the code. For pi, first of all we will check if I mod 2 is equal to 0. If I mod 2 is equal to 0 means it is even. Even philosopher is what? Right-handed. So it will first pick the right chopstick. P chopstick I, and then P chopstick I plus 1 mod n, and then it will eat. Okay, yeah, okay, so before eating we have to check the other thing also. If it is odd, then so if I mod 2 is equal to 0, that means it is even philosopher, else it is odd philosopher. So for else, what we are going to do, so we will say we will do this thing first. Okay, so let me copy this first. Yeah, I think you have got it now. So this means what? It will pick the right chopstick first, and then it will pick the left chopstick. What they are saying, it will pick the left chopstick first, and then it will pick the right chopstick. So I have just imagined these things now. So since it is if even philosopher is picking right chopstick first, that means it is a right-handed person, and then it is picking the left chopstick. And P chopstick I plus 1 modern, that means it is picking the left chopstick, and then it is picking the right chopstick. I think you have got it. So by imagination, I have told you that you can imagine like this, that they are right-handed and left-handed. So even are right-handed and odd are left-handed. Okay, so I think you have got it. Yeah. So after that, they will eat. You can write the code for eating, and then they will do the simple V chopstick. Okay, so V, and they can release in any order. It hardly matters to me because they are releasing now. V chopstick I plus 1 mod n. Okay, yeah. So let me put everything on one slide so that you can note down. Yeah, this is the solution. So now you can imagine, even if all the philosopher wants to eat at a time, there will be no deadlock. Okay, you can check it out yourself. I can put this thing as a homework for you, but let me do it. No problem. Let me do it. So what we are going to say, okay, so we have, let me copy that thing only. Okay, so P1 and then C1. Okay, let me write that. P1, P2, P3, P4, P5. We will have 5 chopsticks. So yeah, C1, then C2, C3, C4, C5. So now if all wants to eat at a time, when deadlock was coming in the previous case, if all the philosopher wants to eat at a time. So here also imagine, if all the philosopher wants to eat at a time, what will be going to happen? So P1 is odd, na? P1 is odd, so it will pick the left chopstick first. So P1 will, I think you already know what is the right chopstick, C1, and what is the left chopstick for P2, P1, C2. Yeah, so P1 is odd. Odd will pick the left chopstick first. That means 2. Okay, P2 is even, so it also wants to pick the even, so it also wants to pick the right chopstick. So P2 also wants to pick C2, but C2 it cannot pick. Why? Because P1 is holding it. Okay, yeah, line by line interrupt I'm imagining now. Please try to focus. P3, what P3 is going to do? P3 is odd. P3 is odd means what? Odd means, yeah, so it will pick the left chopstick. That means it will pick 4. P4 is even, so it cannot pick anything. P5 is odd. P5 is odd, so it want to pick the left chopstick. That means it wants to pick 1. Okay, so P5 will be able to pick 1. Why? Again, I'm repeating, it is odd philosopher. Odd philosopher means this part it will execute. So I plus 1, 5 plus 1, mod 5, 1. So it will pick 1. I think you have got it now. Try to imagine line by line interrupt. That's it. So P1 is you will say odd. So it will come here and it will pick this. After picking it, imagine interrupt P2. P2 even. So it try to pick this thing and we have to imagine interrupt, but it cannot pick it. Why? Because P1 has already picked it. And so on. You can think like that. Okay. So now after line by line interrupt in a circular fashion, P1 will control will come to P1. P1 will try to pick 1, but it cannot pick. Okay, because 1 has been picked by P5, so it cannot eat. P2 is only it wants C2, but C2 is with P1, so it cannot pick. P3 4, and P3 also wants C3. C3 is at you can say nobody is holding C3, so P3 will pick C3 successfully. P5 wants another chopstick 5, and it can pick chopstick number 5 because no other is holding that. P4 will P4 has not picked anything. P2 has not picked anything. P1 is holding only P2. P3 is holding 4 and 3, so it will eat and leave. P5 is holding 1 and 5, so it can successfully eat and leave. Okay, after they left, other philosophers can eat. That's it. So it is deadlock free. It is deadlock free. So I think you have got the point. Okay, so you can take the snapshot of it. That's all for today. So we have completed all the classical problems. In the next lecture, we are going to start deadlocks. Okay, yeah, so background of deadlocks has been completed by your dining philosopher problem. And in the next class, we are going to study deadlocks properly. Okay, yeah, thank you so much. Bye-bye.